Hi, everyone. Thank you for joining our webinar today. With me is Girish and Laryssa. Laryssa is the Associate Product Manager and Girish is the Senior Software Developer. As a team, they have decades of experience in image processing and professional experience developing image analysis solutions for both research and commercial purposes. Laryssa is going to open the floor for us, where she will talk to us about new methods for particle size and shape analysis. And then Girish will take over and dive deeper into the software, which is really the gist and the highlight of all these image analysis. My name is Julie Chen. I am your facilitator, and we'll have a Q&A session at the end of the session. All right, so without further ado, let me go ahead and pass the floor to Laryssa, who is going to speak.
Hi everyone, my name is Laryssa Gorato. I'm the Associate Product Manager to the Eyecon2, and it's a pleasure to be here to deliver this webinar today. Here, I just wanted to make sure that everybody would be aware of what we're going to cover for the webinar. So as you can see, we will discuss a little bit of our background, a little bit of Eyecon2 intro. We will then move it to Girish, and he will talk about an overview of the computation of the parameters. Coming back to me with a little bit of a study, displaying what we are doing with EyePASS version 3.0, how we can export the results, how the new features are used, and how the new results are useful. Moving on to a quick review of everything we've seen and a Q&A session. So a little bit about us. We were founded by Dr. Ian Jones back in 2009, and we are here essentially to bridge the gap between the need of the industry and the need of particle size and shape analysis. We are based in Dublin, Ireland. We evolved into now actually 4 divisions. We started as InnoPharma Labs, and now we have evolved into InnoPharma Technology, Technical Services, InnoGlobal, and InnoPharma Education. We have currently over 120 employees, and we're still growing. But now I would like to let everybody know what Eyecon2 is in a nutshell. It is a particle size and shape analyzer that has been designed to be inline, real-time, non-product contact, so it can be implemented in multiple points of your process. It is designed to analyze bulk solids from 50 microns to 5,500, and we have a multitude of ways of exporting these results. We can carry out the analysis via OPC UA or OPC DA if needed be, and our software EyePASS is 21 CFR and GAM5 compliant, also designed to be ATEX 222 and IP65, and because it has been manufactured here in Europe, it is carrying a CE marking, and we are displaying our results through a PDF report, CSV, multiple types. Now with 3.1, we also have the per particle CSV. All of the images captured that are roughly captured every 5 seconds are exported as a JPEG file, and we are displaying the full particle size distribution from D5 to D95, both in volumetric and numeric measurements. Small particles are a big deal, and here is every way you can implement the unit to your process. I would like to go over the difference between inline, online, at-line, and offline. Because Eyecon is so compact and light, it can be mounted onto your process in different ways. And if you look to our right side of the slide, you will see how it can be mounted in different ways to closely monitor your process. So depending on the process, if it's twin screw granulation or Worcester coating or any other of process, you will preferably implement it in a different way. But back to inline, which is what the Eyecon was designed to be implemented as. It will be directly in contact to a window that is directly connected to your process. If it's an online measurement, it will be done via a bypass to your process. If it's at line, you will be taking off a little bit of sample, and it's usually right beside your process, or offline if you take it elsewhere. Now I'll pass it to Girish.
Yeah, so what I'll do is we'll just quickly look at how the size and shape parameters or measurements are made at a very high level. The size measurements are made first, and the shape parameters are then computed based on the size measurements. So all these measurements that we'll talk about are made on the contour of a particle that's outputted by the chosen detection and segmentation method. So therefore, the accuracy of the measurements is completely dependent on the accuracy of the segmentation. So that's why in developing the previous version of EyePASS, that's version 3.0, we focused on improving the detection and segmentation capability of the software. And that resulted in the introduction of machine learning-based detection and segmentation. So with this robust segmentation as the basis for the measurements, we ensure that the size and shape parameters we introduce in version 3.1 of EyePASS are as accurate as possible. Each of these parameters is computed for every detected particle. So we have this example on screen here. So firstly, from the segmentation contour, we compute the perimeter and the area directly. And then we fit an ellipse to the contour, and that gives us the D1 and D2 measurements, which are the lengths of the major and minor axis of the ellipse respectively. Then we compute the convex hull of the contour. Convex hull, as we all know, is the smallest polygon that contains all the contour points in such a way that joining any two contour points will always be, the line joining any two contour points will always be inside the polygon. So from this convex hull, then we take the convex perimeter. Then we fit two circles to the contour using the contour centroid as the common center. The first one is the inscribing circle, which is the largest circle that can fit completely inside the contour, and the circumscribing circle, which is the smallest circle that encloses the contour completely. So from these circles, we take the radii values. Then we compute the smallest rectangle that encloses the contour. This is called the minimum area bounding box, and it's different from the regular bounding box in that its edges are not necessarily parallel to the X and Y axis. Therefore, this box can be in any orientation. So from this minimum area bounding box, we take the width and the height. So then we move on to computing the Feret diameters, also known as the caliper diameters. So this is the size as measured by calipers along a specified direction, as illustrated here. For making this measurement in the software, we make use of the convex hull. That's because if we consider the contour that's sitting between the set of caliper blades, and we rotate the calipers around the contour, we can see that the blades of the calipers will always sit on the convex hull edges or its vertices. So because the Feret diameter is directional, what we compute are two Feret diameters. One is the maximum Feret diameter, which is measured when the caliper blades are the farthest from each other, and the minimum Feret diameter, which is measured when the caliper blades are the closest to each other. So the next one then, the next diameter that we compute is the Martin diameter, and this is defined as the chord that bisects a given shape. So in this example here, this line is dividing this shape into two equal parts by area. So Martin diameter is also defined along a specified direction. So we compute the Martin diameters along the direction of the two Feret diameters that are already computed. So that gives us the maximum Martin diameter and the minimum Martin diameter. So the last size measurement the last bit that is computed for size measurement is the minimum enclosing square. So this is the smallest square in which the contour can fit. In a two-dimensional world, this box could be seen as the minimum sieve aperture through which the particle would pass. So from all of these size measurements, we report out these size parameters, the D1 and D2, which are the major axis length and the minor axis length of the ellipse, the max and min Feret diameters, the max and min Martin diameters, and the length of the diagonal of the minimum enclosing square. So from all these size measurements, then we also compute shape parameters. These three here are parameters that measure how long a shape is. The first one, eccentricity, it's the ratio of the distance. It's based on the fitted ellipse, and it's defined as the ratio of the distance between the center of the ellipse and either of its two foci to the length of the semi-major axis. So if we start from that definition and simplify it, we end up with this formula here. So eccentricity measures how flat or round the shape of the ellipse is. It is in the 0 to 1 range, and the higher the value, the less the ellipse is like a circle, and therefore the shape is longer. So we see an example, some sample values here, and we see that most of these circular looking particles have lower eccentricity values, but as the particle gets longer, we have higher eccentricity. The next one is aspect ratio, which is also based on the fitted ellipse, and that's simply the ratio of the major axis length to the minor axis length. Its range starts from 1 and is theoretically unbounded because the numerator value is higher than the denominator. The higher the value in this case, the less the ellipse is like a circle, and therefore the shape is longer. And an example here again, where we see that this longer particle has a higher aspect ratio. The last one here, elongation, this is based on the minimum area bounding box and simply the ratio of its dimensions, the width and height, and width being the smaller of the two sides. So it is in the range 0 to 1, and the lower the value of elongation, the longer the shape is. And an example here again, where we see all these circular looking objects have higher elongation value, and this one guy here has a lower value. Then we make then these parameters here that we also compute. These are a measure of how round a shape is. The first one, circularity, it's the ratio of the area of the particle or an object to the area of a circle, which has the same perimeter as the particle's convex perimeter. So from that definition, it simplifies to this formula here. So it is a measure of roundness, but it excludes local boundary irregularities. So it's insensitive to any bumps in the boundaries of the particles. And we can see in this example, so more circular objects have higher circularity values, whereas this guy here has a lower value for circularity. The next one, compactness, it's similar, but it's the ratio of the area of the particle to the area of a circle whose perimeter is the same as the particles or the shapes of the object's perimeter. And that works out to this formula. And that's in the 0 to 1 range as well. And higher values means the object or the particle is more circular. Similar example here, we see the circular looking particles have higher compactness, and this elongated or this ellipse-like object has a lower compactness. The last one here is sphericity, which is based on the two circles that are fitted. So it's simply the ratio of the radius of the inscribing circle to the ratio of the circumscribing circle. It's also in the 0 to 1 range. So sphericity measures the degree to which the particle or an object or a shape approaches the shape of a sphere. So we see an example here again, where this particle here has low sphericity value, and the rest of them, which are more circular, have higher values. The last shape parameter we compute is convexity. So this measures how smooth an object is. So it's simply the ratio of the convex perimeter to the perimeter of the particle itself. So this measures how jagged or bumpy the contour is, and that's also in a 0 to 1 range. So if we look at the same example as we saw earlier, we see in this case all the shapes have high convexity, because even though this is elongated, the boundaries are smooth, so convexity doesn't capture the elongation here. But if you look at a different example where we have different smoothness around the particle contour, we see that this one here, which has really bumpy sort of, the contour is bumpy, you see a lower value for convexity. So all of these shape parameters that we output, it's not necessary that all of them would be useful in all scenarios. So for example, if you look at these shapes here, starting from a perfect circle to ellipses, which are flat to different degrees, and if we try to separate them using say eccentricity, we see that eccentricity can separate the circle, which has an eccentricity value of 0.19. That is separate from the ellipses very well, because all these ellipses have high values for eccentricity. But if you wanted to discriminate between the ellipses themselves, that wouldn't be possible using eccentricity. But if we try elongation, we get some degree of separation between those ellipses. And if we look at the aspect ratios, we see that they're much more separated, because as the ellipse gets longer, the aspect ratio value dramatically increases. Similar to that, if you look at these particles here, and visually they look really different. Their contour shapes are really different. But if you look at the circularity values of these three, they're more or less the same. So we wouldn't be able to use circularity to discriminate between these three particles. But then if you look at the compactness values of the same three particles, we see that this highly bumpy contour particle has a much lower value of compactness compared to the other two, because compactness is sensitive to irregular boundaries. So the main takeaway here is that depending on the application, the material, and the goal of the study or application, we just need to choose the appropriate shape parameter. So with that, I'll hand it back to Laryssa. So we'll go over just more of the results and a mini sort of study on how these parameters and new features will be useful.
Thank you, Girish. So now I just want to go over how we would understand these results and how we can make these new features useful. Why do we need all of these features? Traditionally, the Eyecon2 uses D1 and D2 to determine the best fit ellipse calculated to check all the boundaries of our particles. But we might use Feret's, Martin's projected area diameter, maximum horizontal intercept, and a multitude of other models to demonstrate a tighter correlation between your results and something else. You can see here how we are using it for ourselves now. And D1 and D2 might not always be representative when we're thinking about material that is passing through a sieve, for example. If the material is a little bit more elongated, it will not correlate well with sieve analysis. And essentially, sieve analysis is the most widely known method for particle size distribution. And the issue with that is there's a lot of variability. You have the friability of the material, the friability of the mesh. It's hard to tell if your sieve is drifting, and because of how each operator might do the procedure, you might end up with very different results, and that's not what we want. Still, we use glass beads to calibrate the sieves, and we have compared this glass beads standards to some of our results. Here is a certificate, and the interpolated data from this certificate was used to our study. But first, I would like to quickly inform everyone of our method of operation, how we are detecting the particle and measuring the particle. And through a flash imaging technique, the particle passes through the icon, and an overlay of light of red, green, and blue LEDs will determine the foreground and the background of your sample, as well as the boundaries of the particle. And here I have a quick video that I would like to show you, essentially to demonstrate how we acquired the results. And here you will be able to see glass beads that are standards of the size of 2,800 microns. And before I show you the video, I will let you know how the study was carried out. We used glass beads of 45 microns, 250 microns, 500 microns, and 1,000 microns. All of them were put under the icon, just like this. And we were looking for a correlation between the sieve results and the icon results. Here, I'll show you how to run a session. You will select a configuration. You will give your sample a unique identifier to make sure that you can see this in the future, and that's how we make sure that we are compliant with 21 CFR. Once you select both and you have auto stage and EyePASS running, you will click OK. You will see that the auto stage is moving because your image is changing. You can see the movements changing as well. There I'm highlighting the information that you input. Every time that an image is analyzed, it will change. Before, we only had this 0 to 6,000. Now we have the auto scale. You will notice if you're changing from volumetric to numeric based on the color. So if your histogram is lilac, it means that it's displaying numeric values, and if it's blue, it means that it's volumetric values. You can see the mean, median, the D10, D50, and D90 results on your screen at all times, as well as eccentricity. And you can also input comments to your session. In this case, I'm saying that everything in the session is going well, but let's say you identified something weird about your sample. You can comment that as well, and it will pop up on your reports later. I don't know if I mentioned, but this was a benchtop session, so there wasn't material passing through. It was an aluminum pen under the icon. You don't have to run all the 27 positions. You can run as many as you think it's important, and you can export the results straight from that session or back to session export. You will see PDF files, CSV per particles, and exported images. Every time something exports successfully, a green line will pop up to let you know that it worked. And you can select where it's going to be exported to. I selected that webinar folder. And this is our PDF file. It will show every detail of your sample. If it's an inline sample, it will show the last 300 seconds, because this is, quickly going back, because this is a benchtop session, it will show the entire session. Here you can see an image from the beginning, the middle, and the end of your session. So you know that your focus was adequate and the images you were obtaining were satisfactory. And moving on, you will also see a description of your configuration. So every detail of a config will be reported on your PDF as well. Moving to the images that were exported, this is how you know that everything was as you expected it to be. And now the CSV file. We have the comment we made over there. So any comments you add will pop up on your CSV. And it's a very long one because now we are displaying the volumetric and the numeric results from D5 to D95, as well as all the particle and size parameters that Girish has already mentioned. That's the per particle, and as you can see here, it has the exact same information as the overall CSV particle, but it does that for each individual particle that has been identified by the Eyecon. I just wanted to show you how our images correlate and overlay really well. So via the masked image, you can see how the model is very well behaved and that the results we're obtaining have a very high value and essentially gives us a good confidence that the results are within our expectation. And this is what our CSV file looks like. I have slightly tweaked it so it would fit all in one screen. Everything that is under the green line is either the value that has been displayed or a new shape parameter. So you will see the D1, D2, the eccentricity, aspect ratio, circularity, sphericity, elongation, convexity, compactness, and they are all very important if you want to do something else with your data, which is essentially why a CSV is important. They are light, they are very easy to be manipulated, but in a good way, as in you can extract the information you need, clean the data you need, and turn it into something that you're actually going to use. Here under the green lines, you will also see the ID of the particle and each of those parameters for each of the individual particles that has been detected. This was a snapshot of our results after we have done a little bit of the interpolation between the White House scientific standard results and what we interpolated from the sessions we ran with the Eyecon2. And we have found a very close and very high correlation among all of them. We were trying to find a common denominator for all of the 4 samples, looking for something that would be closer to an equivalent of sieve and the results that we had with the Eyecon. But as expected, that didn't happen because they are 2 different methods of acquiring data, and it's not like for like. You can't expect to see the exact same numbers and the exact same results when you're not using the exact same technique. But we were able to see a very tight correlation and a very close correlation, especially when it came to max Martin diameter. All of our correlated results were higher than 0.8, and overall the 4 samples, we had a higher than 0.9 value when it came to maximum Martin diameter. And because the glass beads are all very symmetrical, and we are planning on moving this study onto a second stage where we will analyze granules and more irregular shapes, so we can trace trend and confirm what we have identified so far with the maximum Martin diameter. Thank you very much for your time. I hope this was as enriching for you as it was a pleasure for us to deliver. And essentially, thank you. If you have any questions, we're here to answer them.
Hey, thank you so much, Laryssa and Girish, for the extensive discussion. So we do have a few questions that came in. Are you ready?
Yeah.
Okay, so how is the size of the caliper used? How is it determined? And then what is the minimum and maximal distances of a particle? Oh, sorry. The minimum and maximum distances of a particle will also vary depending on the caliper sizes. Is that correct?
Yeah, sorry. Yeah. So when we say calipers, keep in mind that the thing I showed on screen is just in a 2-dimensional world. So these are 2D images captured by a 2-dimensional camera. So it's just a projection of a 3D shape. So what I showed as calipers on the screen are just a graphical representation of the algorithm that's pretty much calculating that behind the scenes. So all we have in the 2-dimensional world is a 2D shape. So it's pretty much as Darren mentioned, it's like a bounding box that is rotated around the object, and you just choose the maximum distance as the maximum. You report that out as the maximum Feret diameter, and likewise the minimum one.
Thank you so much. So just let you know that our audience know, Darren is the product manager of the Eyecon instrumentation, and so he's in the background to monitor questions and answers as well. And you might not be able to see it, but hopefully reading it out loud would benefit you as well. Okay, another question is, does this instrument report particle circularity?
Yes, yeah, I believe probably have answered this already. So we saw in one of the slides, if we go to slide 21, Laryssa, sorry.
Yeah.
So we see one of the shape parameters that we compute is circularity. So yeah, so circularity is one of the parameters that we report out. However, different sources have different definitions for circularity. For example, I know that what we call compactness here, image J calls circularity, and some other sources call compactness form factor. So that's why I showed the formula here as well. So people might have different names for this, but as long as we know what we are computing, so it's just to help clarify what we are calculating and the terminology that we use. So yeah, we do report out circularity if one of those two could be the one you're looking for.
Thank you. Can you speak to flow or concentration requirements to use the imager in line? What is usually needed to implement the imager in a flow system?
So I think that I can answer that one. We need to make sure that there is a steady flow of material in front of the window. A few things to be considered about the window are how thick it is and how wide it is. So we would have to discuss what kind of machinery is being used for your process, as well as those. We need to make sure that there is no fouling. So the material has to be constantly moving, and usually 10 meters per second is fine, no faster, no slower than that. But we need to ensure that the material is constantly changing, that what is coming to the window is actually representative of your entire sample, because as I have mentioned, I think on slide here, we present the material to the Eyecon, and with a very quick flash imaging impulse, the red, green, and blue LED will be able to determine what's in the foreground and what is in the background. So if only very fine material is presented against the window, you will be reporting results that are not representative to your sample. So you might be reporting results that are much smaller than what your entire sample is. There is other things that we should consider when we're implementing the Eyecon2 an inline system, but because it's a non-product contact and it was designed to be in real time, we have a lot of confidence that, especially if it's a widely known system as a Worcester coating system or a twin screw granulation system, it should be straightforward to implement. Did I answer your question?
I think so. Some questions are a little bit more complex than the other. You are more than welcome to send us your questions to labinfo@horiba.com. The next question is, what kind of considerations are in place for particles with extremely atypical morphologies, such as fibers?
I'd say that it depends on the size of the fiber. So, and another thing is, we are not fully, I wouldn't say capable, but we need to measure materials that are not rod-like, because if what you see, depending on the variation of the angle, would be completely different, would report false positive. So I'm assuming that fibers might not be measurable yet, but we could work on it.
Thank you. what if you have beads larger than 3 millimeters? Can it be spotted?
It could be spotted as long as it's smaller than 5,500 microns, which would translate to 5.5 millimeters.
Excellent. Thank you very much. And then the next question is, this person's asking that he needs an updated method for particle size, particle analysis and shape. He wanted to know the cost comparison from previous to the existing. So we will certainly reach out to you offline, but this is something that we can talk a little bit more. And again, you can email us at labinfo@horiba.com, or I have your contact info. We'll relay your inquiry to Laryssa or Girish or Darren, who's in the background. The next question is, what is the major difference between software 3.1 and 3.0? And no need to apologize. Some people are joining a little bit later. So do you mind if we need to repeat a little bit, Laryssa and Girish?
No, not at all. EyePASS version 3.0 had a lot of differences when compared to the previous version because it brought to the market machine learning and artificial intelligence. Plus, we are able to add a scale bar to the measurements and a scalable histogram. So it will automatically change to whatever size your particle shape is instead of the previous 0 to 6,000 microns. And on top of all of those, then EyePASS version 3.0.1 still has, we have brought these new particle size and shape parameters and the CSV per particle, so we could provide more resolution to our customers. That way they can tell for each and every particle that has been measured what was the result, not only an overall final result. We still offer that with the traditional CSV, but if they want to investigate their particles closer and if they want to know what their samples are actually like, they can do so through each and every particle that they have seen via the measurement.
That's powerful. Next question. Have you validated the image analysis method against laser diffraction method?
We are currently writing a document comparing our method to sieve analysis and the laser diffraction. I wouldn't go as in comparing them. It's more, what are the limitations? What are the best points for each of those? I don't think that they are that similar to validate against, if that makes sense. We could think of a correlation study, but not a validation against.
I think I can agree. So HORIBA in our particle group, in addition to Eyecon2, we have optical microscopy called a PSA 300 that is more in line to sort of validate the size range that laser diffraction covers, which is essentially from 10 nanometers all the way up to 5 millimeters. So there are definitely pros and cons between the optical microscopy versus what Eyecon can do, which is inline. You can do a bunch of different things offline as well. So that's something that can be done and has been validated on our end. But as far as Eyecon is concerned, it might not be as applicable. So hopefully that helps. The next question is, do you expect the imager to distinguish between agglomerates and dispersed spherical particles?
I don't know if it's the way that the question was worded, but we could pick up on agglomerates. The histogram would spike, the D90 would spike, but I don't know what they mean by the second part of the question.
Let's say if you have two circular particles touching or fused
Also, we're
together?
talking about, we would be able to identify twinning because our D90 would spike, but, and you would be able to see the material that is suffering from twinning on the images that were exported from the session. So yes, we expect to distinguish, but the results wouldn't be, the correct word fails me, but it would all be still displayed as one particle size distribution. It wouldn't be a particle size distribution for material that is dispersed and another for the materials that are twinning, but you would be able to tell because of the D90.
That makes sense. Thank you. Okay, so another question come in. Can we use Eyecon2, this technique, to measure droplet size and emulsion?
Unfortunately, no. The technology is designed for powder bulk solids, and we have essentially begun with the ability of measuring very light and white materials. Now with machine learning and the capability of our models, we have expanded our horizons into material that is darker, but it has to be powder and bulk solid. It can't be in emulsion or in solution. Could be wet, but not in emulsion.
Thank you. So in this case, laser diffraction will be perfect for what your application is. So typically emulsions, we're looking at 100, 150 nanometers. This is a sweet spot for laser diffraction as opposed to image analysis. Next question, can you please explain the setup for twin screw extrusion granulation? And I'll jump in real quick. So there is a separate webinar from the previous 2 years that we've done specifically in twin screw. So I will go ahead and follow up with a webinar recording, but please go ahead. Sorry.
I was just going to say that we have a lot of material and you would probably benefit more from contacting us separately, so we could send you more material on it.
Excellent. We have time for another question. Do you have any mining application? Oh, grinding optimization.
So we had a unit, actually we still have a unit that is specifically used for mining purposes. It wouldn't do anything on its own for grinding optimization because it would only be able to tell how well your grinding system is working, but it would be able to inform you what to do and what areas of your process can be optimized, which is essentially the point of PAT.
Thank you. Girish, do you have anything else that you would like to add before we wrap up?
No, it was thank you for the opportunity. It was a great evening, great way to spend my evening, and yeah, delighted to be presenting.
And thank you, everyone. Thank you so much for the good questions. If you think of anything else, please don't be shy. Just email us at labinfo@horiba.com. For now, have a good evening for those who are in Europe, and thank you, everyone, for joining. Thanks, Laryssa. Thanks, Girish.
Thank you. Good day.
You too. Bye for now.